solutions of the Telegrapher's equations. Now, we found very nice equations that describe voltage and current in independent equations and link the derivatives and time and space, just as a function of a few parameters that we can find in terms of the characteristics of each transmission line. Now, what we want to do next is to find solutions to these equations, and to get started with that, I want you to look at the equations again and just have a very easy example. And the easiest one we can think of is actually a lossless transmission line. So first thing we want to do is we want to look at the equations that we have before. There you see we have the space derivative, time derivative, we've written that down. And just as a reminder, we had the equivalent circuit model where we had an input voltage on the left-hand side and we had resistance, inductance, and of course the shunt loads, which are capacitance and conductance. Put all four of them in there. We can write on the same equation for current as well, just looks the same. Now what we're going to do is to have a lossless line. And what does that mean? If we look into the equation, lossless means our resistance goes to zero, and the same applies to the conductance. So also no losses to ground, so no shunt losses. Now what we get there is, first we can cross out all terms that contain R and G. That means on the time derivative, on the first derivative, both are gone, and also just the simple use, and what stays is the second derivative in space and time. Just write that down once more, because the equation that you're going to see should look quite familiar to you. See here, just second derivative again. Now this is just a simple wave equation, and we can solve that. We have already solved that several times in a very general way. First, we think of an equation that will fulfill that a very general function. We will call it general function f, for example. And we will find that f is just arbitrary. So u is a function of z, of course, which is our one-dimensional parameter, minus speed times time. So speed now is given by, comes from the equation above, square root 1 over square root L prime C prime. So this is the speed of our signal, and we can just have this linear assumption, which will be a general solution that we can fill in there. So this will be our argument, z minus t times speed. Now, what does that mean? We can have an arbitrary function here, and we will have voltage as a function of z, so our space parameter, and we just draw any shape that we can have. And what we'll see is that when we look at this at a later point in time, is that this shape will just have moved with the speed v. So we just have a finite speed, and the shape is just moving as it is, nothing else happens. This is supposed to be the same shape. Sorry for the difference there. Okay, this is one possible solution. Of course, you know, when we have solutions of differential equations, we can superpose them. But for that, we need another solution that is general. So not just f, but we will call the other one g. And what we'll change here is not the linear dependency, but what we will add is the following. So g is then the function of z minus t plus t times v. And that just means that now we have still an arbitrary shape as we had before, but it's not traveling in this direction, but the opposite one. So it's a general solution of these equations, just with the pulse traveling in the opposite direction than what we define as the positive z direction. And now what we can do is a simple superposition of f and g, and that will then be u as a function of z and t equals f, which is traveling along z, plus g, which is traveling in the opposite direction. And this is the first thing we do, just a very general solution that is just based on the assumption that we have a lossless line, and which already looks much simpler than anything we started with. Of course, we still have L and Z in there, which come from the general equation, and we will have to find these based on our calculation. Now, the thing is that we want to use the fact that we usually have AC fields that are kind of sine or cosine waves, so we can have complex wave functions that describe the way that the wave is propagating. And we can solve our partial differential equations with these complex numbers. So some sine shape equation, and you know how these are written. This is just very general. We will have something that's dependent in time, of course, and that has a complex description. And this is usually done by an exponential wave description, as you know. So something that's frequency, which is omega, which is 2 pi times f, just as a reminder. And we'll have then something that takes the form of an exponential function with a complex phasor. So in the exponential, we have some complex number that's also dependent on frequency. And with this, we can transform from the time space, time domain, where we've been before, to the form of frequency space and solve our equation in frequency. Okay, and we will continue in frequency space in the next video.